Hi everyone, I'm happy to present our work, Geometric and Physical Constraints Synergetically Enhance Neural PDE Surrogates. My name is Yunfei, and I work with David Greenberg at the Helmholtz Center, Harlem. Here is the outline of this work. Let's go to the introduction. Partial differential equations are widely used in many different fields. Here is a general PDE with initial and boundary condition. It is usually solved using numerical method, but machine learning approaches have recently become popular. Here we show an example of the PDE surrogate. The input is the previous time step pattern for the neural network, and the output is the pattern for the next time step. Those processes can be repeated. Here we have a question. Why is the neural PDE surrogate important? The answer is that computing is made faster by using machine learning model. For example, using coarser resolution and multiple time steps. This is especially important for climate and ocean, those larger systems. Machine learning model also faced some challenges, such as long-term accuracy, stability, and generalization to new initial conditions. From the mathematical form of PDE, it's possible to derive constraints such as geometric symmetries and conservation laws. Both physical and geometrical constraints have proven using for improving machine learning based on PDE surrogates. However, existing implementations of concentrated architectures generally do not suppose the strategy secrets often used in weather, climate, and flow dynamics, in which variable fields such as pressure, velocity, or density are stored at different locations. Thus, we are faced with a critical scientific question. How can those constraints be imposed on secrets, and would their combination be useful or redundant? So next we go to the network architectures. So first we show the equivariant convolution neural networks. The mathematical form for the equivariant network is written like this. T is the transformation and G is the network. The detailed meaning of this mathematical form can be described as follows. The input goes to the network and then rotates the output. The output is exactly the same as that obtained from the rotated input, and it goes to the same network. Recently, there also has some faster version for this powerful approach. Next, we demonstrate the symmetry of the PDEs. Here we take the example of the incompressible Navier-Stokes. The system is typically solved in using secret strategy. Here we show the symmetry formulas for the rotation and the flip rotation in the bottom. Further, we plot those symmetry for the visualization on the right side. Because the input data is on the cigarettes, so we need to create a special input layer for it. Here we present an example of the input layer for the P4 on the incompressible network stocks. The details of the input layer you can find in our papers. Then output data also need back to on the cigarettes on the end of the network. That's here we show how to build the output layer for P4 and P4M. So furthermore, we propose the physical constraint on the network. We show the formula for the momentum conservation. Then the second one, we learn the scalar potential field in Helmholtz decomposition, where the momentum and mass are conserved for both. Finally, we brought them all together to build our network architecture. We can see that inputs and output on the cigarettes and their internal part is concentrated by symmetry and physical laws. Furthermore, we plot the input equivalent layer for the rotation transformation. So next we show our experiments. So we mainly focus on two PDEs, shallow water equations and incompressible network stocks. The tables shows the list of physical and geometric constraints for each test. So next we go to the result. First, here the result for the shallow water equation. As we can see, the double-concentrated P4MM model obviously improves the prediction compared to the normal CNN without physical constraints. On the right side, we also show some statistical scales, including the mean square error correlation and the mass during the prediction time. It is clearly to show that our P4MM is better than other models. We also presented some details value in the time 1 hour and 25 hours in the table. So next we look at the result of decline turbulence. On the left side, we can see our double concentrated model provides a long stable prediction. Because the turbulence is a chaotic system, the spectrum is widely used to quantify the quality of the prediction in Fourier space. As we can see, our method on the energy spectrum and the momentum is much matching to the reference. The table also shows that our model can improve prediction in the ResNet architecture and the model unit with push forward trick and the model unit with data augmentation. So next we examine the generalization of the shallow water for the shallow water and incompressed Navier-Stokes beyond the training data. We find that a double-concentrated model can improve the prediction beyond the training data for both experiments. The statistical scores also clearly demonstrated this improvement. Next, we also applied our model to prediction ocean current observation. We can see that our double-concentrated model improves the prediction compared to the Lomothian and the previous MM model. Finally, we check the effectiveness of the network and the data set size. Here we're using the incompressible Navier-Stokes for the test. We can find our double-concentrated model is better than Lomothian on the same size of network and data set. Finally, let's go to the conclusion. To summarize, we develop a double-concentrated model with input and output layers on the secrets. We found symmetry is more effective than the physical constraints, but the result was obtained when combining both. Finally, we found that our model can improve the generalization and performance well on the real ocean data. We believe that this combination of the physical constraints and symmetries could be useful in many areas of the science. If you are interested in our work, please go to our paper for details. Thank you for your attention.